Can you imagine this? What if we doubled the Webb telescope's main mirror? You might think it just takes clearer pictures. But that's underestimating it big time. If we had a Webb Plus, scientists could uncover way more cosmic secrets. So can we actually build such a super telescope? Let's look at the current Webb first. Its main mirror is about 6.5 meters wide. It's made of 18 gold-coated hexagon pieces. The total light collecting area is 25 square meters. This makes it over 10 times more sensitive than Hubble in infrared. Doubling the mirror to 13 meters would expand the area to nearly 100 square meters. Its photon gathering power would quadruple. In astronomy, photons are information. The more light you collect, the farther and dimmer objects you can see. But that's not even the main thing. A telescope's resolution scales with mirror size. Double the diameter means twice the resolution. So a blurry blob 10 billion light-years away could show its star-forming regions and gas structures clearly. That is huge. Right now, Webb's farthest view reaches galaxies from 4 to 500 million years after the Big Bang. Their redshift is around 12. With a doubled mirror, sensitivity jumps big time. Redshift could reach 15 or higher. Our view would push to just 300 million years after the Big Bang. That's the era of reionization, when the first stars ignited. This isn't just seeing farther. It's witnessing the universe's earliest stages. Plus, a bigger mirror means better weak signal analysis. This is crucial for studying exoplanet atmospheres. Webb now barely analyzes large planets within hundreds of light-years. But with more light collected, the signal-to-noise ratio improves a lot. We could track smaller, dimmer Earth-like planets. Even half Earth's size. We might study their atmospheric gases. This is super important. Most potentially habitable planets orbit red dwarfs. Red dwarfs are small and dim. Their planetary signals are very weak. Only a big enough mirror can catch their infrared traces. Also, with a larger mirror, scientists get more spectral data from background galaxies. They can map galaxy cluster gravity fields more precisely. This helps chart dark matter distribution in detail. But here's the problem. Can scientists really build this Webb Plus? It sounds awesome, but how hard is it? Let's dive in. First, consider the Ariane 5 rocket. It launched the 6.2-ton Webb to Lagrange point L2, but its max capacity is only 6.5 tons. That launch was already pushing it, so it can't handle a 20-ton or larger infrared scope. The current strongest rocket is SpaceX Falcon Heavy. In expendable mode, it can lift about 63.8 tons to low Earth orbit. In theory, with a good transfer stage, it might deliver a 20-ton Webb Plus to L2. But there are many issues. First, Falcon Heavy's fairing is only 5.2 meters wide. Webb's 6.5-meter mirror was folded tight to fit Ariane's 5.4-meter fairing. A 13-meter mirror can't fit in current fairings. It must be launched in segments and assembled in orbit. Orbital assembly usually happens in low Earth orbit. Low orbit is around 400 kilometers up. Orbital conditions are stable there. Communication delay is low. Robots and astronauts can work together safely. If we go this route, Webb Plus mirror, sunshield and support structure would be split into modules. Multiple rockets would launch them to low orbit. A special orbital platform would use robotic arms for precise assembly and locking. After assembly, a high-thrust transfer stage would be needed. This extra propulsion unit would push the telescope from low orbit to L2. Webb used similar transfer tech, but doing it after orbital assembly is new. It needs propulsion and control systems. The transfer requires continuous burns and course corrections. It takes about a month to reach L2 stable. Why put the scope at L2 instead of low orbit? Infrared observation needs ultra-low thermal noise. L2 is on Earth's night side. Sun, Earth and Moon align almost in one direction. A big sunshield can block solar radiation, plus heat and light from Earth and Moon. This creates a super cold background for the mirror. Webb passively cools to around minus 230 Celsius. This stability is impossible in low orbit. Also, L2 has almost no atmospheric interference or heat reflection effects. Communication windows are clear. It's perfect for deep space infrared observation. So Webb Plus must be at L2 too. This segmented launch and orbital assembly idea is theoretically possible, but engineering-wise it's super complex. In comparison, Starship is the most promising design for this class of mission. It's still in flight and hasn't done any big beyond-Earth jobs yet. But once Starship operates steadily, its lift and fairing space advantages will shine. It could support Moon and Mars missions, and maybe boost next-gen space telescopes. If Starship succeeds in expendable high-performance mode, its low Earth orbit lift could top 200 tons. Its 9-meter fairing gives Webb Plus or even bigger mirrors unprecedented packing space. Bigger telescopes mean deeper cosmic views. Whether humanity enters a new exploration age may depend on next-gen heavy-lift rocket breakthroughs. Make sure to hit that subscribe button, give this video a thumbs up, and share it with your friends and family. Thanks a bunch.